Somewhere in deep space, a black hole is dying. Slowly, atom by atom, it leaks itself back into the dark. And when the last piece flickers away, something impossible happens. Everything that ever fell inside should be gone forever. Every star it swallowed, every memory, every bit of who and what they were. But quantum physics says that can never happen. Information cannot be destroyed. So one of our two greatest theories is lying to us, and whichever one breaks, it changes what reality even is. We're going to follow the light escaping a dying black hole. We will find walls of fire, tiny wormholes, and a universe that might be a hologram. We will reach the edge where space itself dissolves. If this journey rewires your brain, like and subscribe. Stay with us to the end. The clock is running, let's begin. Picture yourself in a canoe, drifting down a wide river toward a waterfall. Far upstream, the water moves slow and calm, and you can paddle back to shore whenever you like. But the closer you drift, the faster the current grabs your little boat. You paddle harder, your arms start to burn. Then you slip across an invisible line on the river, a place where the water rushes faster than you could ever paddle against. Past that line, the fall owns you. You can still see the trees on the bank behind you. You can simply never reach them again. A black hole has a line exactly like that, and scientists have confirmed it is real. They call it the event horizon, and it is the true edge of a black hole, the point of no return. The horizon is pure geometry, a boundary drawn in empty space. You could float right up to it and feel nothing at all. There is no wall, no fence, no glowing sign that says stop. Drift across, and gravity has already won the fight. To climb back out, you would need to move faster than light, and light is the fastest thing that exists. So you stay. You stay forever. That speed is the secret behind everything. At the horizon, the speed you would need to escape climbs all the way up to the speed of light itself, 186,000 miles every single second. Below that line, even a beam of light falls inward and never climbs back. That is the reason a black hole looks black. It is a place where light runs out of the road. Now think about how small these things really are. Take our sun, crush every bit of it down until gravity seals it shut, and the horizon that forms would stretch only about 4 miles across. You could drive from one side to the other in the time it takes to hear this sentence. All that weight, all that fire, folded into a dark ball the size of a small town, smaller than plenty of cities you have driven through. The giant ones tell a different story. At the center of our own galaxy hides a monster 4 million times heavier than the sun. Its horizon spreads far wider than the sun itself, wide enough that whole planets could sail across the edge and vanish without a single ripple. The largest ones we have ever photographed hide behind a horizon bigger than our entire solar system, a shadow you could pour every planet into and still have room to spare. For a long time, that felt like the end of the story. Matter falls in. The horizon seals shut behind it. The black hole grows a little heavier, and the universe quietly loses whatever went inside. Stars, gas, starlight, all of it locked away behind a door that only swings one direction, and every direction inside points deeper in. So cross that edge yourself, and a heavier question starts to pull at you. If nothing can ever climb back out, then where does all of it end up? What waits at the bottom of a well with no floor, sitting in the dark at the very center of the dark? The answer there breaks the laws of physics clean in half. Fall past the horizon, and the falling never really stops. Gravity keeps pulling, and it pulls harder the deeper you go. Soon it grabs your feet stronger than your head, if you are falling feet first. Your feet want to race ahead while your head lags behind. So your whole body stretches, longer and longer, thinner and thinner. Scientists have a nickname for this, and it fits perfectly. They call it spaghettification. You get stretched into a long strand of human spaghetti, then torn apart one atom at a time. But your atoms keep falling too. Everything does. And everything is racing toward the same tiny spot at the very center. That spot has a name. Physicists call it the singularity. It is the place where all the matter that ever fell in gets crushed together into a point with no size at all. Take a mountain, a moon, 1,000,000 suns, and squeeze them down smaller than a grain of sand, then smaller than an atom, then smaller than nothing. That is what general relativity, our best theory of gravity, says happens at the core, and that is where the trouble begins. When physicists plug the singularity into their equations, the math stops making sense. The numbers blow up to infinity. Density, infinite. Gravity, infinite. The curve of space, infinite. Every calculator in the world would flash an error and quit. Infinity is a warning light, flashing to tell scientists that their theory has hit a wall it cannot climb. Think of it like driving a car straight toward a cliff at full speed. Right at the edge, your speedometer, your map, and your steering wheel all go blank at once. The rules you trusted the whole drive suddenly mean nothing. General relativity works beautifully across the entire universe, guiding spacecraft and bending starlight. Drive it to the center of a black hole, and it breaks in your hands. So what actually sits down there? The honest answer is that nobody knows. Not one scientist alive can tell you what the true center of a black hole is really like. The singularity might be a real point. It might be a doorway. It might be something no human has ever imagined, hidden forever behind a horizon that lets no light escape to tell the tale. That is the frustrating part. The one place that could teach us the deepest secret in physics is also the one place we can never see. Any probe we send in falls silent the instant it crosses the edge. Any signal it tries to send back gets dragged inward with it. The universe built a perfect vault, sealed it shut, and threw away the only key. For years, scientists made an uneasy peace with this. The center stays hidden, they figured, and the horizon keeps its secrets sealed. A black hole was a dead thing, a cosmic trash can, sitting still in space and swallowing anything that wandered too close, giving back nothing at all. Then, in the 1970s, a young man in a wheelchair did the math nobody else had bothered to do. He mixed gravity with the strange rules of the very small, and what he found flipped the whole picture upside down. Black holes, he realized, give off a faint light of their own. They glow. The young man was Stephen Hawking, and in the early 1970s he could still speak with his own voice, though his body was already failing him. A disease had begun shutting his muscles down one by one. Doctors had given him only a few years to live when he was barely out of his teens, yet his mind stayed on fire. He could not write equations by hand anymore, so he learned to do them in his head, whole pages of math rolling behind his eyes while the rest of him sat still in a wheelchair. At the time, everyone agreed on one thing about black holes: they only grew. Throw matter in, and they got bigger. There was no way to take anything back out, ever. A black hole was a one-way street, a place where the universe only ever lost. Hawking wanted to test that idea against the rules of the very small, the rules of quantum physics. Nobody had truly mixed the two before. Gravity ruled the huge stuff, stars and galaxies. Quantum physics ruled the tiny stuff, atoms and particles. At the edge of a black hole, both sets of rules had to apply at once, and no one knew what would happen when they collided. So Hawking did the math, and the answer that came back stunned him so much that he thought he had made a mistake. The equation said black holes glow. A faint light seeps out from right near the horizon, a soft radiation leaking into space. It is dim, far too dim for our eyes to catch, colder than almost anything in the universe. But it is real, and it is steady, and it means something enormous. If a black hole gives off light, then it is giving off energy. And energy is the same thing as mass, tied together by the most famous equation ever written. Losing energy means losing weight. A black hole, in other words, leaks itself away. Hawking checked the work again and again looking for the error. There was none. In 1974 he published it, and the world of physics nearly fell out of its chair. The idea was so surprising that many scientists refused to believe it at first. The glow got a name anyway, one it still carries today. They call it Hawking radiation, and almost every physicist alive now agrees it is real, even though it is still too faint for us to measure directly. Sit with what that means for a second. The blackest object in the entire universe, the thing that swallows light and never gives it back, is quietly shining. The perfect trap has a slow leak. The bottomless well is losing water, one drop at a time, into the dark around it. And if it keeps leaking, the ending writes itself. A black hole that loses weight gets smaller. A black hole that gets smaller has less to hold itself together. Give it enough time, an amount of time so vast it barely fits in the mind, and the greatest gravity trap in the cosmos will shrink down to nothing and disappear. The monster is dying. It has been dying since the moment it was born. But this only pushed the mystery deeper. If a black hole shines, where does that light actually come from? Empty space around the horizon holds no stars, no fuel, no fire. So what exactly is glowing? The answer hides inside empty space itself. Empty space is never truly empty. Zoom in closer than any microscope could ever reach, down to the smallest scale that exists, and you find that emptiness is fizzing. Tiny pairs of particles pop into being out of pure nothing, exist for the blink of a blink, then crash back together and vanish. Physicists have measured the effects of this fizzing in their labs, so they know it is real. Empty space is a boiling sea, popping with little sparks of matter that appear and disappear faster than you can imagine. Normally these pairs cancel out perfectly. One particle carries positive energy, its partner carries negative energy, and when they smack back together, the books balance to zero. The universe never notices. It happens trillions of times a second, everywhere, even in the room around you right now, and it all adds up to nothing. Now bring one of these sparks to life right at the edge of a black hole. A pair pops into being straddling the horizon. One partner appears just outside the line, the other appears just inside it, and that changes everything because now they cannot reach each other to cancel out. The inside partner falls, dragged down into the dark, gone for good. The outside partner is suddenly free with no one left to crash into. So it flies off into space as a real particle, a tiny piece of light escaping the greatest trap in the universe. That escaping spark is Hawking's glow. The escape comes at a price. The partner that fell in carried negative energy, the kind that subtracts. When it drops into the black hole, it takes a little bite out of the monster's mass. The black hole pays for every escaping spark with a piece of itself. The glow you see leaking into space is the black hole slowly handing over its own body, one particle at a time. Scientists use this pair's picture as a simple way to see it, and the real math underneath is deeper and stranger. But the ending it points to is solid and agreed upon. The horizon acts like a slow faucet, dripping particles outward into the cold, and each drip costs the black hole a sliver of its weight. Think of the black hole as a giant block of ice sitting in a warm room. It looks solid and permanent, but look closely and it is steaming, giving off a thin mist, shrinking so slowly you would never catch it in the act. Wait long enough, and the mightiest block of ice becomes a puddle, then a damp spot, then nothing but dry floor. A black hole steams in exactly the same way, except its mist is made of a light and particles instead of water, and the faster it shrinks, the stranger the process gets. A smaller black hole is a hotter black hole, glowing brighter and leaking faster than a big one, so the trap does not fade away gently and evenly. It burns slower at first, then quicker still, racing toward its own finish line. Which raises the obvious question: if every black hole is steaming itself away, then how does that final chapter actually play out? What happens in the last moments, when the greatest object in the sky finally runs out of itself to give? The end comes with a flash. The last second in the life of a black hole is the most violent second of all. For most of its existence, a black hole leaks so slowly that the change is almost nothing. A big one, the kind at the centre of a galaxy, gives off a glow so faint and so cold that measuring it is beyond anything we can build. It sits there for ages, barely steaming, sipping away at its own mass one tiny particle at a time. If you watched it for your whole life, you would see no change at all. But the leak feeds on itself. Every particle that escapes makes the black hole a little lighter. A lighter black hole is a smaller black hole, and a smaller black hole strangely runs hotter. It glows brighter and leaks faster than it did before. So the process speeds up. Slowly at first over spans of time that dwarf the age of the universe, then faster still. The smaller it gets, the hotter it burns, and the hotter it burns, the smaller it gets. The two feed each other in a loop that only ends one way. Picture a campfire dying down to a single glowing coal. For hours it sits there, dim and orange and patient. Then, right at the end, the last ember suddenly flares white hot. throws off a bright little burst of sparks and winks out. A black hole ends its life the same way, except the final flare packs more punch than 1 billion nuclear bombs going off at once, all in a single instant. That final blast is one of the few parts of this story we might someday actually catch. If a small black hole somewhere in the sky reaches its last moment while we are watching, our telescopes could see the flash of its death. Scientists are hunting for exactly that signal right now, though so far the sky has stayed quiet. Then, with that flash, it is over. The black hole is gone. Where a monster once sat, bending space and swallowing light, there is now only empty space and a fading burst of radiation drifting off into the dark. The trap has sprung itself. The prison has dissolved with the prisoner still inside, and that is the exact moment the trouble arrives. Everything that ever fell into that black hole is now apparently gone with it. Every star it swallowed, every planet, every cloud of gas, every beam of light it ever caught. All of it went in through a one-way door, got crushed toward the center, and then the whole container evaporated into a faint, featureless glow that seems to carry none of it back. The black hole took its secrets to the grave, and then the grave vanished too. For most objects in the universe, this would raise no alarm. Things get destroyed all the time. But a black hole erasing itself and everything inside it runs straight into one of the deepest rules in all of science. A rule that quantum physics swears can never, ever be broken. Before we reach that rule, though, one number is worth staring at. The dying takes time. A lot of time. So much time that the word slow does not even begin to cover it. Just how long does a black hole take to die? Get ready for a number so large it barely fits inside the human mind. Take a black hole about as heavy as our sun, set it out in the cold of deep space and let it leak away, particle by particle, with nothing falling in to feed it. How long until it steams itself down to nothing? The answer is a 1 followed by 67 zeros. That many years. Try to picture that. The universe itself is only about 14 billion years old. Written out, 14 billion is a 1 with 10 digits trailing behind it. The lifetime of a sun-sized black hole has 67 digits. To reach the end of even one black hole's life, you would have to let the entire history of the universe, all 14 billion years of it, replay from the beginning until now, over and over, more times than there are grains of sand on every beach on Earth. And you still would not be close. The whole age of the cosmos, next to a black hole's lifespan, is less than a single blink in a life that lasts 100 years. It is barely the first tick of a clock that runs almost forever. And the giant black holes take far, far longer. The monster at the center of our galaxy, 4 million times heavier than the Sun, would need something like a 1 followed by 100 zeros to fully die. There is a word for a 1 with 100 zeros. It is called a googol, and it is larger than the count of every atom in the observable universe, many times over. Write that number out and it fills a whole line of the page, 100 zeros marching one after another after another. No clock ever built could count that high. So when scientists say black holes evaporate, they do not mean any time soon. They mean a future so distant that the stars will have long since burned out. Every galaxy will have gone dark. The universe will be a cold, black, empty place, drifting and silent. And the black holes will still be there. The last lights in creation, glowing faintly, taking their unimaginable time to fade. They will be the final objects left in existence. When the very last one finally flickers out, in a far future almost too far to name, the cosmos will hold nothing but thin, cold radiation spread across the dark. That is the deep future waiting at the end of this story. But black holes grip physicists for a reason far deeper than their lifespan. They matter because of what they carry away when they finally go. Here is the collision the whole mystery is built on. When a black hole evaporates, it seems to erase everything that fell inside. And there is a law in physics, one of the most trusted laws we have, that says erasing is impossible. Truly, completely impossible. The universe, this law insists, must keep a perfect memory of everything. Two ideas, both proven true, both tested 1,000 times, cannot both survive this moment. one of them has to give. So what is this law that black holes seem to break? Why are scientists so certain that the universe can never truly lose anything? Not a single scrap. Not one bit. The answer is the deepest rule in all of quantum physics. Quantum physics has one rule it guards above almost all others. The universe keeps perfect records. Scientists call the thing being recorded information. Every particle in existence carries information, a full description of what it is and how it moves, its own tiny story written into the fabric of reality. And the deepest law of the quantum world says that story can never be wiped out. You can scramble it, hide it, tear it into a million pieces and scatter them across the galaxy. But somewhere, in principle, the full story always survives, waiting to be read back. This rule sits at the very foundation of quantum physics, as solid as any idea in science, holding up the whole structure like a keystone in an arch. Pull it out and everything collapses. Every prediction scientists make about atoms, lasers, computer chips, and the light from distant stars leans on this one idea. The universe does not forget. To feel how strong the rule is, imagine the universe as a movie playing forward. Quantum physics says you could always, in theory, run that movie backward. Watch smoke gather itself back into a cigarette. Watch a shattered glass leap up off the floor and pull itself whole. In the real world, these things never happen, because the odds are impossibly against them. But the deepest laws allow it. The information about how everything started is still there in the ending, complete enough that a perfect rewind could rebuild the past exactly. That is what physicists mean when they say information is conserved. The present always holds the full recipe of the past. Nothing ever gets truly, permanently lost. Take a simpler picture. Imagine you have a deck of cards in perfect order, ace to king, every suit in its place. Now shuffle it for an hour until the order looks completely random. The deck seems like pure chaos. But the information is all still there. Every card is present, and if you tracked every shuffle perfectly, you could undo them one by one and bring the deck right back to where it started. Shuffling hides the order, it never destroys it. The universe, quantum physics insists, works the same way. It shuffles constantly, mixing everything into what looks like noise. Yet the original order is always buried in there somewhere, recoverable in principle if you were clever and patient enough. The cards are only ever rearranged, never removed from the deck, and this is exactly why black holes cause such panic. Everything that falls into a black hole is made of particles, and every one of those particles carries its story, the same as everything else. When they cross the horizon and get crushed toward the center, that information should still exist somewhere. The rule demands it. Scramble the story, sure. Shuffle it beyond all recognition, fine. But erase it completely? The universe is not supposed to be able to do that. Then the black hole evaporates. It steams away into a faint glow and disappears. And when scientists look closely at that escaping glow, they find something that stops them cold. The light coming out looks totally random, like a deck shuffled into pure noise, except this time the shuffle looks impossible to undo. The order gone, the recipe gone, every path back sealed off. The story that fell in looks truly, permanently gone, and that should be impossible. The word information sounds like something from a computer, but in physics it means something much wider. Information is simply the full set of facts about a thing, where every piece of it sits, how fast each piece moves, which way it spins. Bundle all of that together and you have the complete description of an object, its true and total story. A cup of coffee has information. So does a star, a snowflake, a sneeze, and you. Everything that exists carries a description of itself written in the positions and motions of its particles. The key idea is that scrambled and gone are two completely different things, and mixing them up is where confusion begins. Scrambled means the information is messy, jumbled, spread out, and hard to read. But it is all still there. Gone means the information has vanished from the universe entirely, wiped out, impossible to recover no matter how clever you are. Quantum physics happily allows the first, it flatly forbids the second. Picture a sandcastle on the beach. A wave rolls in and knocks it flat, leaving a lumpy patch of wet sand. The castle looks destroyed, but think about what really happened. Every grain that made up those towers is still lying right there on the beach. Not one single grain vanished. The shape is scrambled, sure, smeared into a mess. Yet if you could track exactly where every grain went, and exactly how the water pushed each one, you could in principle reverse the whole thing and rebuild the castle grain by grain. That is scrambled. The pattern is wrecked, but the pieces all remain, and the full story hides inside the mess. Now imagine something far stranger. Imagine the wave rolls in, and the sandcastle simply blinks out of the universe. Not knocked over, not buried, just gone, every grain erased, as if it had never been there at all, leaving behind not even empty space where it stood. No grains to find, no way, ever, by any method to bring it back. That is gone. And in the entire history of physics, scientists have never once seen it happen. Not to a sandcastle, not to a burning log, not to anything. Every time something looks destroyed, the pieces and their story turn out to still be there, hiding in the smoke and ash and scattered bits. The universe scrambles constantly. It shuffles, smears and mixes without stopping. But it never crosses that final line into true erasing. That is the promise quantum physics makes, and every experiment ever run has kept that promise. Which brings us back to the black hole and its faint escaping glow. When Hawking first worked out what that glow should look like, the answer he got was chilling. The light leaking out looked truly random. The same dull hiss no matter what fell in, with none of the hidden order that a knocked-over sandcastle keeps. A star, a spaceship, a library full of books, drop any of them into the black hole and the escaping glow looked identical, featureless, blank. If that is right, then the black hole is doing the one thing the universe is never allowed to do. It is erasing the story, wiping the sandcastle clean out of existence. Hawking's own math had aimed a loaded gun straight at the heart of quantum physics, and someone was going to have to figure out who fired. Look closely at Hawking's glow, and one detail makes the whole crisis snap into focus. The light escaping a black hole depends on almost nothing about what fell in. Feed the black hole a star made of hydrogen, and the glow comes out a certain way. Feed it a star made of iron instead, or a cloud of dust, or a fleet of spaceships, and the glow comes out looking exactly the same. The only thing that changes the glow is the black hole's total weight, its spin and its charge. 3 simple numbers. That is all the escaping light seems to remember. Physicists have a blunt way of saying this. A black hole, they say, has no hair. Strip away every detail of whatever fell inside, every difference and feature and quirk, and all that survives on the outside are those 3 plain numbers. Everything else looks smoothed away, bald, erased. Sit with how wild that is. 2 black holes could be built from completely different things. One swallows a galaxy of ordinary stars, the other swallows a galaxy of pure antimatter, or a trillion diaries, or the entire internet. If they end up with the same weight, spin and charge, they look identical from outside, and they give off the exact same featureless glow as they die. So when the black hole finishes evaporating, the glow that carried its energy away carried no clues about the contents. The star and the antimatter and the diaries all leave the same blank hiss behind, and once the black hole is gone, there is nowhere else for the information to be. The inside is gone. The horizon is gone. Only that plain, featureless radiation remains, drifting off into the dark. The same whether it came from books or bombs or stars. The story that fell in has vanished from the universe, truly gone in the way that quantum physics swears can never happen. This is the black hole information paradox, and it is one of the sharpest puzzles in all of science. 2 ideas, both rock solid on their own, are pointing loaded guns at each other. On one side stands Einstein's theory of gravity, which describes the black hole and its one-way horizon. That theory has passed every test we have ever thrown at it, bending starlight and steering spacecraft with flawless aim. It says the glow is featureless, and the information is lost. On the other side stands quantum physics, which rules the world of the very small with the same perfect record. Not one experiment in a century has ever caught it breaking, and it says flatly that information can never be lost. Both theories work, both are trusted completely. And in the belly of a dying black hole, They call each other liars. Something has to break. Either Einstein's gravity is missing a crucial piece near the horizon, and the glow secretly carries the story out after all, or quantum physics is wrong at its very foundation, and the universe really can erase things forever. Whichever one falls, it takes a piece of our understanding of reality down with it. For years, most physicists could not even agree on which side was right. The smartest people alive stared at the same equations and walked away with opposite answers. Some were so sure the information was lost that they were willing to bet on it, in public, with witnesses, and a few of them did exactly that. To understand why the smartest people on Earth lose sleep over a dying black hole, you have to see how good these two theories really are. Start with Einstein's gravity. When he wrote it down over a century ago, it made a wild prediction. Gravity should bend the path of light, so a star's spot in the sky would shift when its light passed near the sun. Scientists tested it during an eclipse, and the starlight bent by exactly the amount he predicted. Since then, it has passed every single test. It guides the satellites that run the maps on your phone, correcting their clocks so precisely that without it, your navigation would drift off by miles every day. A few years ago, scientists even caught two black holes crashing together 1 billion light-years away. By feeling the tiny ripple it sent through space, a ripple Einstein's math had described 100 years earlier. The stretch they measured was smaller than the width of a single atom, and the theory nailed it. Now take quantum physics, the rules of the very small. It is, without exaggeration, the most tested and most successful theory humans have ever built. One of its predictions about how an electron behaves in a magnetic field has been checked against experiment out to more than 10 decimal places, and it matches. That is like measuring the distance from New York to Los Angeles and being right down to the width of a human hair. Every phone, every computer chip, every laser and solar panel and medical scanner works, because these strange quantum rules hold true every time, without fail. So both of these theories are giants. Each one has stood for a century. Each one has been tested to a razor's edge and never once cracked. Scientists trust them the way you trust the ground under your feet. The horrible part is that these two giants disagree. For almost everything in the universe, they never have to talk to each other. Gravity handles the huge and heavy, the planets and stars and galaxies. Quantum physics handles the tiny and light, the atoms and particles. Their worlds barely touch, so their argument stays hidden and quiet. A black hole drags them into the same room and forces them to fight. It is huge and heavy, so gravity rules it. But its horizon works on the tiny scale, where quantum rules take over. Right there at the edge, both theories have to describe the same patch of reality at the same time, and they hand back answers that cannot both be true. One says the information burns away, the other says burning it is forbidden. This is why physicists care so much. The paradox is a crack, and through that crack they can see something enormous hiding underneath. Somewhere below both of our great theories, there has to be a single deeper theory that holds them both and settles the fight. A theory of everything, the holy grail of physics, the thing Einstein chased for the last 30 years of his life and never found. The dying black hole is a keyhole. Peer through it, solve the paradox, and you might glimpse the deepest layer of reality, the bedrock rules that everything else is built on top of. To get there, scientists first had to sharpen the question until it was almost unbearable, and the sharpest version of it came wrapped in a strange little story about a burning book. Stephen Hawking loved to explain the paradox with a book on fire. Take an ordinary book, he would say, and throw it into a fireplace. The flames eat the pages, the cover curls and blackens. Soon the whole thing is ash and smoke, and the words you could read a minute ago are gone. Every letter, every sentence, every idea seemingly wiped out by the fire. But physics tells a stranger truth. That book still exists, in a way you would never guess. The information in the book still exists, scattered now into the smoke, the ash, the heat, and the faint light of the flames. If you were a godlike being who could measure every puff of smoke and every glowing ember with perfect care and track exactly how each one moved, you could in principle read the entire book back out of the fire. Every word would be recoverable from the pattern of the ash and the colour of the light. The burning scrambled the book into a horrible mess, but it never truly erased a single letter. That is the promise quantum physics makes about everything in the universe. Burn it, smash it, dissolve it in acid, and the story survives somewhere in the wreckage. The pieces scatter, but they never blink out of existence. In theory, always in theory, you could gather them up and rewind. Now throw that same book into a black hole instead of a fireplace. At first it looks like the same story. The book crosses the horizon and gets torn apart, crushed toward the centre, scrambled into a mess just like the fire would do. Fine. No problem yet. Wait around, and the black hole slowly steams away into Hawking's faint glow, the way the fire turned the book to smoke and light. So a godlike being should be able to read the book back out of that glow, exactly the way they could read it out of the smoke, right? That is where the two stories split apart. When Hawking studied his glow, the light leaking from a black hole looked truly featureless. The same dull hiss whether you fed it a book or a brick or a bell. The smoke from a fire carries the book's fingerprints in every swirl. The glow from a black hole seemed to carry no fingerprints at all. Read it as carefully as you like, and the book is simply not in there to be found. A fire scrambles the story. A black hole, if Hawking was right, erases it. Same looking process, wildly different ending, and the difference is the whole crisis in a single picture. This little tale did something powerful. It took a paradox buried in pages of frightening math and made it something anyone could feel in their gut. Everybody knows that burning a book destroys it in the everyday sense. Learning that physics says the story survives the fire, and then learning that a black hole might break even that rule makes the stakes suddenly clear. Hawking believed, for a long time, that the black hole truly won, that the book was gone for good and the universe really could forget. He was so convinced that he did something scientists love to do when they are certain. He made a bet, a public one, with a famous rival and a very unusual prize on the line. In 1997, three of the greatest minds in physics made a wager. On one side stood Stephen Hawking and a fellow physicist named Kip Thorne, a longtime friend who studied black holes with him. They took the bold position. Information that falls into a black hole, they bet, is truly destroyed. The universe forgets. Gravity wins and quantum physics has to bend. On the other side stood a physicist named John Preskill. He refused to believe it. Information cannot be lost, he insisted, no matter how strange the black hole gets. Somehow, some way, the story has to come back out in the glow. The quantum rule holds, and it is gravity that has a piece missing. They wrote the bet down and signed it, the way people have made friendly wagers among scientists for centuries, and they picked a prize that fit the theme perfectly. The loser would buy the winner an encyclopedia, a book packed with information from which facts can always be looked up and recovered at will. A cheeky nod to the whole fight. Whoever was wrong about information escaping would hand over a fat volume stuffed full of the stuff. Then the argument raged on for years. This was more than a game. Both men were staking their scientific judgment in public, in front of the whole field, on one of the steepest questions anyone had ever asked. Losing meant admitting your gut instinct about the universe had been wrong. Slowly, the ground began to shift under Hawking's feet. New work in physics, especially a set of stunning discoveries about how gravity and quantum rules fit together, started to tilt the odds. More and more, the math hinted that the information did survive somehow, hidden in the glow in a way too subtle for Hawking's first calculation to catch. In 2004, at a big physics conference, Stephen Hawking stood up in front of the world and did something rare for a scientist of his fame. He admitted he had been wrong. The information, he now believed, does escape the black hole after all. It comes out in the glow, scrambled beyond recognition, but still there. The way words survive in the smoke of a burning book. He conceded the bet to John Preskill and handed him his prize, a thick encyclopedia of baseball, joking that the winner could pull any fact out of it whenever he liked. Kip Thorne, though, was not ready to give in. He never conceded his half of the bet. To him, the case was still open, the proof not yet solid enough to surrender, and in a way, he had a point. Hawking had changed his mind, but he had not fully shown, step by step, exactly how the information got out. He had a strong hunch and a pile of supporting clues. The airtight proof was still missing. So even with the most famous voice in the argument switching sides, the paradox was far from solved. Believing the information escapes is one thing. Showing the exact escape route, the precise path the story takes to sneak out of a black hole, is something much harder. And when physicists first tried to trace that route, they slammed straight into a rule that seemed to make the whole escape impossible. You cannot simply copy the answer to safety. If the information sneaks out of a black hole, the obvious hiding place is the glow itself. Think back to Hawking's first calculation. He looked at the escaping light and saw pure randomness, the same dull hiss no matter what fell in. But his calculation used some rough approximations. It treated each escaping particle on its own, one at a time, without carefully tracking how all of them might be linked together. And that is where the escape plan lives. Maybe the information lives in the connections between the particles, rather than inside any single one of them. Picture a long text message sent one letter at a time. If you only ever look at single letters, floating alone, they look like meaningless noise. A T here, an H there, an E somewhere else. Random junk. But line all the letters up in the right order, and suddenly they spell out a sentence. The meaning was never inside any one letter. It lived in the pattern, the way the letters related to each other across the whole message. The glow from a black hole might work the same way. Each particle, looked at alone, seems random, just as Hawking found. But look at the entire stream of escaping particles together. Study how every piece connects to every other piece, and the hidden message might appear. The story of everything that fell in could be smeared across the whole glow, spelled out in the subtle links between billions and billions of tiny sparks of light. If that is true, then Hawking's original answer was simply incomplete. He caught the randomness of the single letters and missed the sentence hiding in the pattern. The information was leaking out the entire time, tucked into connections too faint for the first rough math to notice. This idea gave physicists real hope. It meant they could keep both quantum physics and Einstein's gravity. They just had to show that the glow was more subtle than it first appeared, carrying its secret cargo in the fine print of how its particles line up. But a monster problem lurks in this plan, and it comes from one of the strictest rules in all of quantum physics. The story that fell into the black hole still exists inside, at least until the very end, crushed and scrambled near the center. And now this escape plan says a copy of that same story is also leaking out in the glow, so the information seems to be in two places at once, inside the black hole and outside in the radiation. That sounds harmless enough. Making a backup copy is the most ordinary thing in the world. Your phone does it every night. Yet the quantum world flatly forbids it. There is an ironclad law, proven and unbreakable, that says you cannot copy quantum information. You cannot make a perfect duplicate of a quantum story. Not ever, not by any trick. It is one of the deepest rules the small-scale world obeys. So the escape plan runs head-first into a wall. The information cannot be inside and outside at the same time, because that would mean two copies exist, and two copies are forbidden. To get out of this trap, physicists had to bend their minds around one of the strangest rules in science. The rule that says you can never clone a single quantum bit. Quantum physics guards a rule that sounds almost silly until you see why it matters. You cannot copy a quantum thing. In the everyday world, copying is everywhere. You photocopy a page, you screenshot a picture, you save a file twice. The original stays put, and now a perfect twin exists beside it. Nothing about that feels strange, because the world you live in copies things all day long without blinking. The quantum world slams that door shut. Down at the scale of single particles, there is a proven law that says a quantum state can never be perfectly duplicated. Take one particle carrying some quantum information, and nothing in the universe can produce a second particle in the exact same state while leaving the first one untouched. No machine, no method, no clever trick can pull it off. Scientists proved this beyond doubt decades ago, and it holds without a single exception. They call it the rule against cloning. Why would nature bother forbidding something so useful? The answer reaches deep into how the quantum world works. Measuring a quantum thing changes it. The moment you look closely enough to copy a particle's full state, your looking disturbs that state and scrambles part of it. So the perfect copy you wanted slips away the instant you reach for it. The universe protects its quantum secrets by making them impossible to peek at without smudging the original. This rule holds up huge chunks of modern science. It is the reason a future quantum computer could keep information secure in ways no ordinary computer ever could. Break the no cloning rule, and a big part of quantum physics falls apart with it. Now carry that rule back to the black hole and feel the trap snap shut. The escape plan needed the information to be in two places, crushed inside the black hole near the center, and also leaking out in the glow. 2 copies of the same story, one in, one out. But the rule against cloning says 2 perfect copies of a quantum story can never exist. So the escape plan, as it stands, is simply against the law. Either the information stays locked inside and never escapes, which breaks quantum physics by erasing it when the black hole dies, or the information escapes in the glow, which seems to break quantum physics a different way by making a forbidden copy. Every road leads off a cliff. This is the knot that made the paradox feel truly hopeless for a while. It was no longer just gravity arguing with quantum physics. Now quantum physics seemed to be arguing with itself. One of its own rules demanded that information survive. Another of its own rules seemed to forbid the only way it could survive. Picture being told you must keep a treasure safe forever, and also that you're never allowed to make a backup of it, and also that the vault holding it will one day vanish into thin air. Every instruction on its own makes sense. Together they seem impossible to obey all at once. For a real solution, physicists needed a clever escape from this trap, a way to satisfy every rule without breaking any of them. And the first big clue came from asking a sharper question about exactly when the information has to start showing up in the glow. That question has a precise and startling answer. If information really does leak out of a black hole, there is a precise moment when it has to begin, and that moment has a name. A physicist named Don Page found it in the early 1990s, so scientists call it the Page time. It marks the halfway point in the life of an evaporating black hole, measured in a special way, and it splits the whole story into 2 acts. To see why the halfway mark matters, think about the black hole and its glow as a pair of partners tied together by an invisible thread. Every time a particle escapes as part of the glow, it stays secretly linked to the black hole it came from, connected by one of the strangest features in all of quantum physics, a bond that ties 2 distant particles into a single shared state. As more and more particles escape, more and more threads stretch between the growing cloud of glow and the shrinking black hole. In the first act, before the Page time, the black hole is still big and still holds most of the information inside. The glow escaping so far looks almost perfectly random, carrying very little of the story with it. Every escaping particle just adds another thread, and the tangle of connections between the glow and the black hole keeps growing thicker. So far, this matches what Hawking always said. The early glow really does look like meaningless noise. Then the black hole crosses the halfway line, and the second act begins. Now something has to change, for a simple reason. The black hole is shrinking fast. It has less and less room left inside to store information. Past the halfway point, it becomes too small to keep hiding the full story, so the information has no choice. It has to start pouring out into the glow, faster and faster, if quantum physics is going to be obeyed. Page worked out that if information is truly conserved, then right around this halfway moment, the glow must switch from looking random to secretly carrying the story back out. The featureless hiss of the early glow has to give way to a later glow quietly loaded with information, until by the very end, everything that fell in has come back out, written into the pattern of the escaping light. This gave physicists something priceless, a sharp, testable prediction about how a black hole should behave if quantum physics wins. Watch the amount of hidden connection between the black hole and its glow, and track it from the birth of the black hole all the way to its death. If information is saved, that quantity should rise for the first half of the black hole's life, reach a peak right at the Page time, then fall back down to nothing as the last of the story escapes. If instead Hawking's original picture is right, and information is truly lost, that same quantity should only ever climb higher and higher and stay high forever. It would still be sky high at the moment the black hole vanishes, proving the story was trapped inside and erased. So the whole paradox boils down to the shape of a single line on a graph. One path rises and falls, the other rises and stays. Whichever shape reality actually follows tells us if the universe remembers or forgets. Scientists gave that make or break line a name of its own. And for decades, drawing it correctly was the hardest problem in the field. The line that decides everything is called the Page curve, and its shape is the whole ballgame. Imagine a graph. Along the bottom runs time, from the moment the black hole forms to the moment it dies. Up the side, the graph tracks a single quantity, a measure of how much hidden quantum connection ties the escaping glow to the black hole. It rises as the black hole and its glow get more and more tangled together, and it falls as that tangle comes undone. Two very different lines could fill that graph, and only one of them can be true. The first line is Hawking's. Follow his original math, and the quantity does one thing only. It climbs. Every particle that escapes adds another thread of connection, so the line goes up and up, steady and relentless, all the way to the end. When the black hole finally vanishes, the line is still riding high, frozen at its peak. That high value is the smoking gun of lost information. It says the story never came back out, that it stayed tangled inside until the black hole erased it. Hawking's line is a ramp that only ever goes up. The second line is pages. Follow the rule that information must be saved, and the line tells a completely different tale. For the first half of the black hole's life, it climbs, exactly like Hawking's, as the early glow tangles up with the black hole. But at the halfway point, the page time, it reaches a peak and turns. From there, it heads back down, falling as fast as it climbed until it hits the floor at 0 right when the black hole disappears. 0 means the story fully escaped, with nothing left trapped and nothing erased, the information all carried safely out in the glow. Page's line is a mountain, rising to a peak and coming back down the other side. So there they sit, two lines on the same graph, a ramp and a mountain. One says the universe forgets, the other says the universe remembers, and reality follows only one of them. This turned a foggy worry into something razor sharp. The entire information paradox, all the confusion about burning books and vanishing sandcastles, now came down to a single question a child could ask while looking at a drawing. Does the line come back down, or does it stay up? For a long time, this was maddening. Hawking's math clearly produced the ramp, the line that goes up and stays up. His calculation was careful and trusted, and it stubbornly refused to bend the line back down. Yet nearly every physicist had become convinced, from a dozen other clues, that the real answer had to be the mountain. They believed in Page's curve in their bones. They simply could not derive it. Their best, most direct math kept giving them the wrong shape. For almost 40 years, that was the wall. Everyone knew what the answer should look like, and no one could make the equations produce it. The Page curve was a target painted on the sky, clear as day, and every arrow scientists fired sailed straight past it. Then someone found a way to make the line bend. But the path they took to get there was so strange, it made the paradox itself look simple. It started with a single, radical idea. Maybe the same reality can hold two completely different, equally true stories at once. The radical idea that crack the door open sounds impossible. Two different observers can see two different versions of the same event, and both are right. Physicists call this black hole complementarity, and one of its champions was a bold, guitar-playing theorist named Leonard Susskind, who spent years going toe-to-toe with Hawking over this very puzzle. The idea starts with a simple question. What actually happens to an astronaut who falls into a black hole? And the strange answer is that it depends entirely on who is watching. Imagine two people. One is the astronaut falling feet first toward the horizon. The other is a friend staying safely far away, watching through a powerful telescope. From the astronaut's point of view, crossing the horizon is a quiet event. For a big black hole, there is no wall, no fire, no sudden jolt. The astronaut sails right across the edge without noticing anything special and keeps falling inward toward the center, carrying all their information with them, straight into the black hole. For this falling observer, the story is simple. The information goes in. Now switch to the friend watching from far away. They see something completely different. As the astronaut approaches the horizon, the friend sees them slow down, stretch out, and freeze, as if time itself is grinding to a halt at the edge. The astronaut never quite seems to cross. Instead, they appear to spread out and smear across the surface of the horizon, heating up in the glow. From the friend's point of view, the astronaut and all their information get smeared onto the outside of the black hole and later leak back out in the escaping radiation. For this distant observer, the story is also simple. The information stays outside and comes back out. So which one is telling the truth? Does the information fall in, or does it stay out? Complementarity gives a wild answer. Both are true, and there is no contradiction, because no single person can ever check both stories against each other. The astronaut who fell in cannot climb back out to compare notes with the friend. The friend can never see inside the horizon to check on the astronaut. The two versions of reality can never be laid side by side, so they are allowed to disagree. This dissolves the cloning problem in one clean stroke. Earlier, the trap was that information seemed to be in two places at once, inside the black hole and outside in the glow, and copying is forbidden. Complementarity says the two pictures never share a single reality. There is one copy for the falling astronaut safe inside, and one copy for the distant friend out in the glow. Since nobody can ever hold both pictures at the same time, the universe never actually makes a forbidden duplicate. The rule stays safe. It is a bit like a courtroom with two witnesses who saw the same crime from opposite sides of a wall. Their stories sound like they clash. But because neither witness could see through the wall, neither can prove the other wrong, and both accounts can stand. For a while, this felt like a beautiful patch on the whole mess. Reality gets to have two versions, each observer keeps their own steady story, and the dreaded copy machine never runs. Then someone asked a sharper question about the falling astronaut. What exactly does that astronaut feel at the very instant they cross the horizon? And the answer that came back set the peaceful edge of a black hole on fire. Fall toward a giant black hole, and the edge should feel like nothing at all. That was the whole promise of Einstein's gravity. The horizon of a big black hole is a calm, empty place. Cross it, and you should feel no bump, no heat, no sign that anything has changed. You would sail right through, still breathing, still alive, with the point of no return already behind you. For 100 years, every physicist trusted that picture. Falling through a horizon is supposed to be smooth and quiet. Then, in 2012, 4 physicists did a careful calculation and found something that made the whole field go pale. They followed 3 rules everyone believed at once. Information escapes in the glow, so quantum physics survives. The horizon is calm and empty, so Einstein survives. And the deep rules of entanglement, the strange links between particles, hold true as always. Line up all 3, run the math, and they smash into each other. The 3 cannot all be right. Something has to break. And the answer the calculation pointed to was terrifying. The horizon might be a wall of fire. The calculation said an astronaut falling in could hit a blazing sheet of raw energy right at the horizon, particles screaming at unthinkable temperatures, hot enough to burn them to nothing in an instant. A sudden wall of fire waiting exactly where Einstein promised there would be peace. Physicists gave it a blunt name. They call it the firewall. Feel how bad this is. To save quantum physics and let the information escape, the math seemed to demand a firewall at the edge. But a firewall wrecks Einstein's gravity, which insists the horizon of a big black hole is a smooth, ordinary place where nothing special happens. You cannot have both a peaceful horizon and a wall of fire in the same spot. So the paradox came roaring back, meaner than before. For years, complementarity had felt like a clever peace treaty, letting 2 observers keep their own stories. The firewall tore that treaty up. It said the price of saving information might be setting the horizon ablaze and burning Einstein's beautiful theory along with the astronaut. This split the world of physics down the middle. Some brilliant scientists decided the firewall must be real, and the horizon truly is deadly. Others rejected it outright, sure that a smooth horizon had to survive somehow, and that the calculation was missing a crucial trick. Nobody could agree, and the disagreement dragged on for years. Some of the most famous names in the field publicly changed their minds more than once, wrestling with the horror of it. Stephen Hawking himself weighed in, suggesting the whole idea of a sharp horizon might need to go. The argument grew so heated that people started calling it a crisis, a genuine emergency at the foundations of physics. At the very center of the firewall fight sits one strange, stubborn rule about entanglement. It is the rule that forced the fire into the calculation in the first place, and it sounds almost like a law about love and loyalty. A particle can be fully bonded to one partner. It can never be fully bonded to 2 at once. Break that idea open, and you find the true heart of the whole crisis. To see why a wall of fire showed up in the math, you have to meet the strangest link in all of physics, Take two particles and connect them in a special quantum way. Now they share a single fate. Measure one, and you instantly know something about the other, no matter how far apart they drift. Send one to the far side of the galaxy and keep the other in your pocket, and they stay tied together, two ends of the same invisible thread. Scientists call this entanglement, and they have proven it real in the lab thousands of times. It is one of the most tested and most bizarre facts about our world. Entanglement comes with a strict rule, and physicists compare it to loyalty and love. If two particles are fully entangled with each other, giving all of themselves to that one bond, then neither of them has anything left to share with a third. A particle can pour its whole quantum heart into one partner. It cannot pour that same heart into two partners at the same time. The bond is exclusive. Scientists call this the monogamy of entanglement, and it never bends. Picture a friendship bracelet made of a single strand. Tie both ends tightly to one friend and you have used up the whole strand with nothing left over for anyone else. To bond with a second friend, you would have to loosen the first knot. Full loyalty to one leaves nothing for another. Now bring this rule to the edge of a black hole and watch the trap close. Remember the escaping glow. Every particle that flies out started as one half of a pair, born right at the horizon, with its partner falling inward. To keep the horizon calm and smooth the way Einstein demands, that escaping particle must stay fully entangled with its infalling partner. Full bond right across the edge. That smooth bond is what makes the crossing feel like nothing. But quantum physics also needs the information to escape. And for the story to come out, each late particle of the glow has to be fully entangled with the whole cloud of earlier radiation that left before it. That is how the hidden message gets carried out. Spelled in the links between old glow and new glow, there is the problem. The same escaping particle is being asked to be fully entangled with two different things at once, fully bonded to its infalling partner to keep the horizon smooth, and fully bonded to the early radiation to carry the information out. The monogamy rule flatly forbids this. A particle cannot give its whole self to two partners, so one bond has to break. Break the bond with the early radiation, and the information stays trapped, and quantum physics dies. Break the bond with the infalling partner, and the smooth horizon shatters, replaced by that violent wall of fire, and Einstein dies. That is the firewall laid bare. A single overworked particle asked to love two partners completely, forced by the rules to betray one of them. Whichever bond snaps, one of our great theories falls with it. For a while, this looked like a dead end, with every escape leading to a wall. The way through came from a place nobody expected. It started with a question about how much a black hole can actually remember. How much can a black hole remember? The question sounds simple, but the answer rewired how physicists think about reality itself. In the early 1970s, a young graduate student named Jacob Bekenstein started asking it, and his own famous advisor told him he was probably wrong. Bekenstein pushed ahead anyway, and what he found became one of the deepest clues in the whole mystery. Think of any storage you know: a phone, a hard drive, a library. The more room it has inside, the more it can hold. A bigger box fits more stuff. So you would expect a black hole to store information based on its volume, the space packed inside its horizon. Double the room inside, store twice as much. That feels obvious. Bekenstein found something stranger and far more beautiful. A black hole's memory depends on the size of its surface, the area of the horizon wrapped around it, and the room inside makes no difference at all. All the information a black hole can hold is written across its outer edge, like words on the skin of a balloon. Let that reshape your picture of a black hole. Imagine a library where every book ever written is somehow recorded only on the outside walls, and the entire inside of the building is off limits to the records. The bigger the walls, the more books. The vast space inside stores nothing. That is how a black hole keeps its memory, painted entirely on its surface. The record lives in the skin, never in the belly, and the amount it can store is staggering. The horizon is tiled into unimaginably tiny squares, each one far smaller than an atom, smaller than almost anything has a right to be. Every one of those tiny squares holds a single bit of information, one yes or no, one basic piece of a story. Count the squares across the whole surface of a real black hole, and the number of bits is larger than all the storage humanity has ever built, by more than you could ever write down. This matters enormously for the paradox. If everything that fell into the black hole is somehow recorded on the horizon, then the information was never truly lost inside after all. It was sitting on the surface the whole time, waiting, like a message written on the outside of a sealed box. And as the horizon slowly steams away in Hawking's glow, that surface writing could peel off bit by bit and float out into space, carried away in the escaping light. The horizon, in other words, might be the black hole's hard drive, a thin skin of memory, holding the complete story of everything it ever swallowed, ready to hand it all back as it evaporates. This one idea planted a seed that grew into something enormous. If a roomy three-dimensional black hole stores all its information on a two-dimensional surface, then a solid thing is being fully described by a flat boundary around it. The inside is captured completely by the edge. Push that thought as far as it will go and it stops being just about black holes. It starts whispering something wild about the entire universe, about you, about the space you're sitting in right now. Maybe everything around you is written on a distant surface too. Take the black hole's secret and aim it at everything, and you get one of the boldest ideas in modern science. Two physicists working in the 1990s asked a daring question. If a black hole stores all its information on its two-dimensional surface, why should any region of space be different? Maybe every chunk of the universe works the same way. Maybe the full contents of any volume can be captured completely on the flat boundary that surrounds it. They called this the holographic principle, and the name comes from a familiar object. A hologram is a flat piece of film, just a two-dimensional surface. Yet when you shine light on it, a full three-dimensional image floats up out of it. The depth, the roundness, the sense of a solid object, all of it hides inside the flat sheet. The surface holds the whole scene. The holographic principle says our universe might pull the same trick. Everything happening inside a region of space, every particle, every force, every event, could be written in complete detail on the boundary wrapped around that region. The inside would be like the floating image, the boundary would be the film, and the boundary always has one fewer dimension than the space it describes. Sit with how strange that is. It suggests that a flat surface with less room and fewer directions can hold every last detail of a fatter, roomier world. Nothing gets lost in the translation. The surface is a perfect, complete copy, written in a different language on one less dimension. Try a picture to feel it. Imagine your whole bedroom, every object in it, the bed, the lamp, the air, even you, fully described by a pattern painted on the walls and floor and ceiling around you. The three-dimensional room and the two-dimensional shell holding it are two ways of telling the exact same story. Change something in the room, and the pattern on the walls changes to match. Change the pattern on the walls, and the room inside changes. They rise and fall together, locked as one, two versions of a single truth. If this is true, it flips our sense of what is real. We feel like we live inside a roomy three-dimensional world, with depth and distance stretching around us. The holographic principle hints that all of it could be encoded on a faraway surface, a thin boundary at the edge of everything, and that the depth we feel is a kind of projection rising from that flatter, more basic reality. For a while, this was a wild guess, a beautiful hunch with no hard proof behind it. Bekenstein's black hole made it plausible, but plausible is a long way from certain. Physicists needed something stronger. They needed an actual working example, a case where they could prove, with real math, that a world with gravity inside was exactly the same as a flat boundary with no gravity around it. In 1997, a young physicist found exactly that. He built a toy universe you could hold in your imagination like a bottle, and he showed that everything inside it was perfectly described by particles dancing on the glass. His discovery became the most studied idea in all of theoretical physics, and it turned the hologram from a dream into a tool. The young physicist was Juan Maldacena, and in 1997 he wrote down a result so powerful it changed the course of physics. Maldacena studied a special kind of toy universe. Picture a giant glass bottle. Inside the bottle is a world with gravity, where space can bend and black holes can form, a small model of the kind of universe Einstein described. On the surface of the bottle, the glass itself lives a completely different thing. A swarm of particles obeying only the rules of the very small with no gravity at all. Then Maldacena proved something breathtaking. The world of gravity inside the bottle and the swarm of particles on the glass are the exact same thing. Every event inside, every bending of space, every black hole that forms and dies, shows up perfectly as a pattern of particles dancing on the surface. Ask a question about the gravity world inside, and you can answer it by studying the flat glass instead. Two descriptions, one reality, told in different languages on different numbers of dimensions. This was the holographic principle made solid, a working and provable example. A universe with gravity, fully captured by a flat boundary without gravity. The hologram was real, at least inside Maldacena's bottle. Physicists pounced on it. Here, finally, was a place where they could study black holes with total control. Any confusing question about a black hole inside the bottle became a question about ordinary particles on the surface, and the particles on the surface follow the plain rules of quantum physics, where information can never be lost. That last part landed like a thunderclap. On the glass surface there is no black hole and no gravity, just particles obeying quantum rules that keep perfect records. Nothing there can erase information, ever. But the surface tells the exact same story as the inside. So if the surface never loses information, then the black hole inside the bottle can never lose it either. The hologram had settled the argument, in this toy universe at least. Information survives. It has to. A black hole can form inside the bottle, swallow whatever it likes, and evaporate away, and the whole time, out on the glass, the story stays safe and complete in the dance of the particles. There is simply nowhere for it to vanish to. Hawking's fear of true erasing could not survive in Maldacena's bottle. The math was airtight. But a nagging gap remained, and it kept physicists up at night. They now knew, for certain, that the information gets out. The surface proved it. What they still could not see was how. Watching from inside the bottle, staring at the black hole and its faint glow, the escape route stayed hidden. They knew the answer was yes, and they still could not trace the path. It was like knowing a magician's trick must have a secret, because the impossible clearly happened, while still having no idea how the rabbit got into the hat. The surface swore the information escaped. The inside refused to show the method. To find that method, physicists needed one more wild idea, maybe the wildest of them all. It tied together two things Einstein had discovered decades apart, two ideas he never dreamed were connected. Wormholes and the ghostly link between entangled particles might be one and the same. Long before black holes made headlines, Einstein left behind two strange ideas, published just months apart, that seemed to have nothing to do with each other. The first was the wormhole. Einstein and a partner showed that his gravity equations allowed a bizarre shortcut through space, a tunnel linking two faraway places, so you might step in near one star and step out near another, skipping all the distance between. For decades, wormholes lived mostly in the math and in science fiction, beautiful and probably impossible to use. The second was entanglement, that ghostly link between two particles that share a single fate no matter how far apart they sit. Einstein hated this one. He called it spooky and thought it revealed something broken in quantum physics, yet experiment after experiment proved entanglement real. The spooky link exists. For 80 years, these two ideas sat in separate drawers. One was about the shape of space, giant tunnels and shortcuts. The other was about the quantum links between tiny particles. Nobody imagined they were related. Then, in 2013, two physicists made a jaw-dropping suggestion. What if wormholes and entanglement are secretly the same thing? What if every pair of entangled particles is connected by its own tiny wormhole, a microscopic tunnel through space too small to ever crawl through, but real all the same? This idea says the spooky link Einstein hated, and the space tunnels he discovered are two faces of one deeper truth. Entangle two particles, and you have quietly built a thread of geometry between them, a whisper of a wormhole. Bundle enough entangled particles together, and those countless threads could weave into a wormhole big enough to notice. Connection between particles becomes connection through space. Picture two distant islands with open water between them and no bridge. Now imagine that every time two people from the islands become close friends, a tiny invisible plank appears stretched across the water. One friendship, one flimsy plank far too thin to walk on. But let thousands of friendships form, thousands of planks piling up side by side, and slowly a solid bridge takes shape wide enough to drive across. The bridge was built entirely out of the connections between people. That is what this idea says about space itself. The bridges of the universe, the tunnels and the very fabric between things, might be built out of entanglement, out of countless tiny quantum links stitched together. If that is true, it hands physicists a stunning new way to think about the black hole. The escaping glow is entangled with the black hole it came from, and if entanglement means a wormhole, then the black hole and its own radiation are joined by a hidden tunnel through space, a secret passage connecting the trap to the light leaking out of it. Suddenly the escape route stops being a matter of magic and becomes a matter of geometry. The information would never need to smash through the horizon or break any rule. It could slip along the wormhole bridge that entanglement quietly built, from deep inside the black hole to the glow far outside. For years this was a gorgeous idea with no proof, a poem more than a theorem. Then a small group of physicists sat down to actually calculate what those wormholes do to a black hole's memory, and the answer bent the impossible curve. Follow that hidden bridge over the whole life of a black hole, and it grows in a way that changes everything. At the start, when the black hole is young, only a little glow has escaped. The cloud of radiation drifting away is small, and it holds just a few threads of connection back to the black hole. The bridge between them, woven from those threads, is thin and short. It barely reaches anywhere. In these early days, the radiation knows almost nothing about what is trapped inside. It looks like meaningless noise, exactly as Hawking found. But the glow keeps leaking particle after particle, year after unimaginable year. The cloud of escaped radiation grows larger and larger, and every new particle adds fresh threads of entanglement between the cloud and the shrinking black hole. The bridge thickens, it lengthens. Slowly, quietly, the wormhole tying the radiation to the black hole is becoming a serious piece of geometry, a real tunnel gaining strength with every drop of glow. For the first half of the black hole's life, the bridge still stays outside. It links the radiation to the surface of the black hole, yet it cannot reach past the horizon into the hidden interior. The deep inside, where the swallowed stars and secrets are crushed, stays walled off. The radiation is connected to the black hole, but only to its outer skin. Then the black hole crosses the halfway line, the page time, and the bridge finally grows long enough to do something astonishing. It reaches inside. Past the halfway point, the wormhole built by all that piled up entanglement stretches so far that it plunges through the horizon and into the interior. The cloud of radiation, drifting far out in space, suddenly has a tunnel connecting it to a region deep within the black hole. And through that tunnel, a piece of the inside starts to belong to the outside. Picture a rescue rope thrown toward a canyon. At first the rope is short, tied only to the near cliff edge, useless for reaching anyone stranded on the far side. But imagine the rope grows on its own, lengthening day by day, until at last it stretches across and drops down into the canyon itself, close enough to loop around someone trapped at the bottom. The moment it reaches them, they're connected to safety, even though they never moved. That is what happens to the information deep inside the black hole. For the first half of the story, it sits trapped in the interior, out of reach. Then the growing bridge arrives, drops into the interior, and suddenly that trapped information is roped to the radiation far outside. It can be pulled to safety along the tunnel that entanglement built. This is the turning point the whole paradox was waiting for. The escape route is a wormhole that grows with time, staying outside at first, then plunging inward at the halfway mark to grab the buried story and carry it out. Physicists gave the captured piece of interior a strange and fitting name. They call it an island, a lonely patch of the inside, cut off by the horizon, that secretly counts as part of the outside world. And working out how that island behaves is what finally cracked the paradox open. The island might be the strangest object in this entire story. An island is a chunk of space sitting deep inside the black hole, past the horizon, in the region no signal can escape. By every ordinary rule, it belongs to the inside, cut off from the universe forever. Yet the math of the growing wormhole says something that sounds impossible. That inside chunk secretly counts as part of the outside. It belongs to the radiation drifting far away in space. Read that again slowly, because it breaks how we think space works. A region locked inside a black hole is at the same time part of the world outside the black hole. The island lives in two places at once. It sits crushed in the interior, and it also belongs to the faint glow that escaped long ago and floated off into the dark. How can a piece of the inside also be the outside? Through the bridge. The wormhole built by all that entanglement ties the deep interior to the distant radiation so tightly that the two become one system. Whatever is written on the island is also written in the glow. Read the radiation carefully enough, and you're reading the island too, even though it hides behind a horizon light years away. Try a picture. Imagine a spy trapped in a sealed cell with no doors and no windows. It looks like nothing about that spy could ever reach the outside. But the spy has a partner in a distant city, and the two share a secret so complete, so perfectly matched, that knowing everything about the partner tells you everything about the spy. Study the free partner, and you learn the prisoner's every thought. The cell walls stop mattering. The secret leaks out through the perfect link without any door. The island works like that trapped spy. The horizon is the cell wall. The radiation is the partner in the distant city. And the bond between them is so complete that the sealed interior spills its whole story into the glow outside, walls or no walls. This is what finally lets the information escape while every rule stays whole. It never has to smash through the horizon. It never gets copied into two forbidden twins. The interior simply belongs to the radiation through the bridge, so as the black hole evaporates and the glow carries its cargo away, the island goes with it. The buried story rides out on the very light everyone thought was empty, and there is a precise rule for when the island appears. Before the page time, before the halfway mark, there is no island. The bridge is too short to reach inside, so the radiation holds no piece of the interior, and the glow really is close to empty. After the page time, the island switches on. The bridge plunges in, claims its patch of the interior, and from that moment the radiation carries the growing story of everything the black hole ate. That switch, from no island to island, is the exact moment the glow stops being noise and starts carrying the secret out. It is the turning point Page predicted, now with a real mechanism behind it. To actually calculate all this, physicists had to use a trick so bizarre it sounds made up. They imagined many identical black holes at once, copies standing side by side. And when those copies were allowed to connect, a new kind of wormhole appeared. The trick that cracked the paradox open sounds like something out of a fever dream. To measure one black hole, physicists imagined many. The problem was this: to work out how much of the story the radiation carries, scientists needed to calculate a certain hard quantity, a measure of entanglement, and the direct math kept spitting out the wrong answer, Hawking's ramp that only climbs. So they reached for an old and clever shortcut. Instead of studying one black hole, they studied several identical copies of it side by side, ran the calculation on the whole group, and planned to work back to the single real one at the end. Physicists call these copies replicas, and the trick had cracked hard problems before. Then something wonderful and unexpected happened. When they lined up the identical black holes, the equations of gravity did something no one told them to do. New tunnels appeared. Fresh wormholes reached out and connected the separate copies, bridging one black hole to the next, stitching all the replicas together through hidden geometry. Nobody put these tunnels in by hand. Gravity conjured them on its own, insisting they belonged in the calculation. Scientists named them replica wormholes. At first, these extra tunnels seemed like a nuisance, strange bridges cluttering the math, but their effect was staggering. In the early life of the black hole, the replica wormholes stayed weak and barely mattered, so the answer looked just like Hawking's, a rising ramp. Then, right around the page time, the wormholes between the copies grew strong and took over the calculation. And when they took over, they dragged the answer down. The curve bent. For the first time ever, a calculation rooted in gravity produced the falling half of the mountain. The line climbed, reached its peak at the halfway mark, then turned and came back down towards zero, exactly the shape Page had predicted 40 years earlier and no one could derive. The the replica wormholes were the missing ingredient. They were the reason the information comes back out. Think of it like a chorus of singers who seem to sing alone. Measure them one at a time and you hear only noise, each voice wandering off on its own. But the singers are secretly linked, listening to each other. And when you finally account for those hidden links, the separate voices lock into harmony and a clear song rises up. The replica wormholes are those hidden links between the copies, the connection that turns noise into a tune, chaos into the page curve. What makes this so shocking is where the wormholes came from. Nobody chose to add them. The plain trusted math of gravity, the same math physicists had used for decades, contained these extra tunnels all along. They had simply been ignored, thrown away as too weird to count. Once scientists stopped ignoring them and let gravity have its full say, the paradox that had haunted physics for almost 50 years began to dissolve. The universe, it turned out, had been holding the answer inside its own equations the entire time, waiting for someone brave enough to keep every strange term. In 2019, two separate teams working an ocean apart reached this result at nearly the same moment. Neither knew how close the other was, and when their papers landed, the field understood that something historic had just occurred. The page curve had finally been derived. For almost 50 years, the black hole had been winning. In 2019, physics finally struck back. When the two teams bent the curve, they did more than solve a math puzzle. They showed, with real gravity equations, that a black hole gives its information back. The story that falls in comes back out in the glow. Hawking's original fear, that the universe could truly forget, lost its grip. Quantum physics held. The books balance. Nothing is erased. It is hard to overstate what a moment this was. A problem that had stumped the greatest minds for 2 generations, that had launched 1,000 arguments and a famous bet that had made brilliant people doubt the foundations of reality finally cracked. The escaping glow was proven to carry the secret out. Hidden in the pattern, smuggled through the growing bridge, revealed by the wormholes gravity had been hiding in plain sight. Somewhere, if he could have seen it, Hawking would have grinned. His own radiation, the thing that started the whole crisis, turned out to be the very messenger carrying the information to safety. The trap he discovered was also the escape hatch. The glow gives, and the glow takes away, and in the end it hands everything back. Now for the honest part, because good science never oversells a win. This triumph came inside simplified, carefully chosen model universes, cousins of Maldacina's bottle, where the math could be tamed. Physicists have not yet run the full calculation for a real black hole hanging in our own messy, expanding universe. The core result feels solid, and almost everyone believes it points the right way. But the complete story, worked out for the actual sky above us, is still being written. There are also deep puzzles left inside the victory. The replica wormholes work beautifully in the equations, yet nobody fully agrees on what they truly mean. Are they real tunnels between real copies of a black hole? Are they a clever bookkeeping trick standing in for something we do not yet grasp? The math clearly works. The meaning underneath it stays slippery. So the paradox is cracked, though not sealed shut forever. Think of it like reaching the summit of a mountain that blocked the trail for decades, only to see, from the top, a whole new range of peaks stretching out beyond. The wall is behind us. Fresh mysteries wait ahead, taller and stranger than before. Still, the direction is clear now, and it points somewhere breathtaking. To make the information escape, physicists had to accept that a chunk of a black hole's inside secretly lives in radiation far away. They had to let wormholes sprout from ordinary gravity. They had to treat entanglement as a kind of glue that builds bridges through space. Each of those moves chips at something we always took for granted. The simple idea that space is just a fixed stage, and that near and far are solid, separate things. Follow these ideas to their end, and they suggest something wilder than the original paradox. Space itself, the distance between things, the very fabric you move through, may not be the bottom layer of reality at all. It may be built from something deeper. The next clue says that space is woven, thread by thread, out of entanglement. Pull those threads, and the stage itself starts to come apart. What if the space around you is something knitted together out of quantum threads, rather than the bottom layer of reality? A physicist named Mark van Ramsdonk asked exactly this, and the thought experiment he ran is simple enough to picture. Start with the holographic idea, a boundary surface describing a space with gravity inside. Now imagine slowly cutting the entanglement between two halves of that boundary surface, snipping the quantum threads that link one side to the other, thread by thread. As he cut, something remarkable happened in the space inside. The two regions it described began to drift apart. The more entanglement he removed, the farther the two chunks of space separated, and the thinner the bridge of space between them became. Keep cutting. Remove the last thread, and the space pinches in the middle and tears clean in two, leaving two separate universes that can never touch. Run the experiment backward, and the message is clear. Entanglement is what holds space together. Two regions sit close and connected because their quantum threads are strong. Two regions sit far apart because their threads are weak. Distance itself, the plane gap between here and there, might be nothing more than a measure of how entangled two places are. Picture a vast net made of countless tiny elastic bands, each one linking two nearby points. When the bands are tight and strong, they pull the points close, and the net is dense and solid, a smooth surface you could walk across. Snip some bands, and the points they held drift apart, opening gaps and holes. Snip enough, and the net falls into loose, disconnected pieces. Space, in this view, is that net. The elastic bands are entanglement. Pull the threads, and the fabric of space itself loosens and comes apart. This flips the usual story on its head. The usual story puts space first, a fixed stage, with particles as the actors moving around on top of it. Van Ramsdonk's picture says the entanglement between particles comes first, and space is the stage that grows out of it, stitched together by those quantum links. Space is the end product, woven together thread by thread rather than laid down at the start. If that is right, then the smooth, solid world we live in, the distances we cross, the room we move through, all of it emerges from a deeper web of quantum connections underneath. What feels like empty space between two objects is really a thick tangle of entanglement, holding them at just that distance. Remove the tangle, and the very notion of distance between them would lose all meaning. This idea explains why black holes were so confusing. A black hole twists space into knots and rips it in ways that broke our theories. But if space is made of entanglement, then the wild behavior near a black hole is really the behavior of entanglement being stretched, torn, and rewoven. The bending of space and the shuffling of quantum links become one and the same event, described in two languages. The paradox forced this lesson on us. To let information escape, physicists had to treat space as something built, something that grows, rather than a fixed floor beneath everything. And once you see space that way, an even stranger truth about the black hole clicks into place. The inside of the black hole may already be sitting out here, woven into the glow itself. The interior was never as far away as it looked. The inside of a black hole may already be sitting out in the open, woven into the glow escaping it. The island result showed the first hint. A patch of the deep interior sealed behind the horizon secretly belongs to the radiation drifting far away. But push the thought further, and it gets stranger still. If space is built from entanglement, and the interior is fully entangled with the escaped glow, then the interior is spread out inside that radiation, encoded in the pattern of particles that already left, rather than waiting behind the horizon to be reached. This means the black hole may have no true inside, in the way we normally picture insides. When you imagine a black hole, you probably see a dark ball, with a hidden region tucked deep within, a secret room behind a locked door. This new picture says the secret room is an illusion of perspective. The stuff you thought was locked deep inside is actually smeared across the glow that escaped, out in open space in front of you the whole time. Try a comparison. Imagine a book that has been perfectly memorized by 1,000 people, scattered across the world, then the only paper copy burns to ash. Where is the book now? It is gone from the shelf, with no pages left to hold. Yet the book still exists, spread across 1,000 minds. recoverable if you gather what each person knows. The book has no single location anymore. It lives in the pattern of everyone who carries a piece of it. The inside of an evaporating black hole works like that scattered book. Its interior has no single hiding place. It lives in the pattern of the radiation, in the web of entanglement stretched across the escaped glow. The deep inside and the faraway outside turn out to be two descriptions of one shared thing. There is only one story, told once from within and once from without. This is the deepest twist in the whole story. For decades, the horizon looked like a hard wall between two separate worlds, the trapped inside and the free outside. The new picture erases that wall. The inside and the outside are stitched together so completely that the interior is quietly present in the exterior, folded into the light we can see. It also finally kills the copying problem for good. Earlier, the fear was that information sat in two forbidden places, once inside and once in the glow. Now we understand there were never two copies. There is one thing, described two ways. The interior and the radiation are the same information wearing two different masks, and a single thing cannot be an illegal copy of itself. The horizon, then, works more like a trick of the light than a wall, a line that looks like it separates two worlds while secretly joining them. What falls in was never truly cut off. It was folded into the outside, hidden in plain view, riding the glow. If the inside can quietly live in the outside, then the whole idea of here and there, of near and far, starts to wobble. Two things we call far apart might secretly be the same place. And once distance itself stops being solid, the last comfortable rule of the universe begins to crack. Everything you do rests on one quiet assumption. Things far away cannot instantly affect things right here. Physicists call this idea locality, and it is the backbone of common sense. What happens on the far side of the galaxy stays on the far side of the galaxy. To change something, you have to reach it, touch it, send a signal that travels across the distance between. Near things influence near things. Faraway things stay out of reach until something crosses the gap. The whole world seems to run on this rule. Black holes are quietly tearing it apart. The island result says a chunk of a black hole's deep interior is stored right now in radiation that floated away ages ago and sits light years off in space. The information about that hidden inside region lives far away too, out in the distant glow, as much as it lives inside. One piece of reality, held in two spots separated by an enormous gulf, with no ordinary bridge running between them across normal space. That should not be possible in a world built on locality. Here, the deep interior and the faraway radiation act like a single connected thing, even though a vast emptiness lies between them. Poke the radiation, and in a real sense you are poking the black hole's insides. The gap between them, all those light years, stops behaving like a true separation. This lines up with the lesson that space is woven from entanglement. If distance is just a measure of how entangled two places are, then two regions with a powerful hidden bond can be deeply connected no matter how far apart they look on a map. The map says far, the entanglement says close, and the entanglement is what is real underneath. Picture two friends who finish each other's sentences, know each other's moods before a word is spoken, and somehow always call at the same moment. Put an ocean between them and the bond does not fade. On a map they sit thousands of miles apart. In every way that matters, they are right next to each other. The physical distance becomes almost a lie about how connected they truly are. The universe, black holes suggest, is threaded with connections like that. Deep bonds that ignore how far apart things sit in plain space. The tidy grid of here and there, near and far, may be a surface appearance, a convenient story that mostly works, laid over a reality where the true closeness of two things is set by their entanglement. This does not mean you can send a message across the galaxy in an instant, or break the cosmic speed limit. The rules are subtle, and they still protect cause and effect in the ways that count. But at the deepest level, the simple picture of a universe neatly divided into separate, independent places is starting to look like a rough sketch rather than the true map. Locality, one of the most trusted ideas in all of physics, may hold only as an approximation, a story that works in everyday life and quietly fails near a black hole. So the paradox has led us somewhere staggering. Chasing a single beam of escaping light, we have watched the inside blur into the outside and distance lose its grip. Yet a stubborn question still hangs over all of it. What if the whole rescue is wrong, and the information really is lost after all? For all the triumph, a stubborn band of physicists keeps asking the uncomfortable question. What if the information really is destroyed, and every clever rescue is fooling itself? This deserves to be taken seriously because the winning story leans on some wild moves. It asks us to believe that wormholes sprout from plain gravity, that a piece of the inside secretly lives in the outside, that space is woven from entanglement. Each of those ideas is strange enough to make a careful scientist pause. Maybe, the skeptics say, all this cleverness is a house of cards, and the simpler answer was right all along. The black hole eats the information, evaporates, and the story is gone, truly gone, wiped from the universe with no way back. If that is the truth, the cost is enormous, and that cost is exactly why most physicists resist it. Losing information means the deepest rule of quantum physics fails. The universe would no longer keep perfect records. You could no longer, even in principle, rewind the movie of the past. Cause and effect would develop a leak, a place where things vanish without a trace and history cannot be reconstructed. Some scientists have tried other escape routes to dodge this. One idea says the black hole never fully evaporates. Instead, it stops shrinking near the very end and leaves behind a tiny frozen nugget, a leftover speck that quietly holds all the trapped information forever. Nothing is lost in this view, because the black hole never truly finishes dying. It just becomes a permanent information-stuffed crumb, sitting in space for all time. Other thinkers have floated even wilder options. Maybe the information slips into a brand new baby universe that buds off from the black hole's core, carried away into a space we can never visit or check. Maybe our rules simply break down in ways we have not imagined yet. Each idea trades one strange price for another. The honest state of things is that no single answer has fully won. The wormhole story with its bending page curve is the front runner, and most physicists now bet on it. But it lives in simplified toy universes, and a handful of respected scientists still think the whole approach could be missing something deep. Science moves forward on evidence, and the final ironclad evidence, drawn from a real black hole in a real sky, is still out of reach. That is what makes this frontier so alive. These are working scientists arguing right now, in papers and lecture halls, over a question with no settled answer. The person who finally proves how information escapes a real black hole, or proves that it truly cannot, has not yet spoken. They might be alive today. They might be a teenager somewhere staring up at the night sky, about to fall in love with a puzzle that has no back-of-the-book solution. Because whichever way this breaks, the stakes could not be higher. If the rescue holds, reality is deeply stitched together in ways we're only beginning to map. If the information is truly lost, then something we treated as sacred, the promise that the universe never forgets, is broken. And a broken universe would mean far more than one failed rule. It would change what it means for anything to be real. Suppose the skeptics are right, and information really can be destroyed. What would that actually break? Start with prediction. The deepest rule of quantum physics is the reason the universe is knowable at all. Because information is never lost, the present always contains the full recipe of the past and the seeds of the future. Know enough about now, and the rules let you work out what came before and what comes next. That single promise is what makes science possible. It is why an experiment done today will come out the same tomorrow, why the laws hold steady, why the universe behaves like something you can figure out. Let information truly vanish, and that promise cracks. If pieces of reality can drop out of existence with no trace, then the present no longer holds the whole story. Gaps open in the record. The past becomes partly unknowable, impossible to reconstruct no matter how perfectly you measure. The future grows fuzzier too because some of what shapes it has leaked away into nothing. The universe stops being a machine you can fully read and starts hiding permanent blank spots. It gets worse. Physicists showed that if black holes erase information, the damage spreads far beyond the black hole itself. The same leak that lets information vanish would let energy appear and disappear at random, everywhere, all the time. Empty space would sizzle with sudden bursts of heat coming from nowhere. This steady, dependable universe we count on would turn jittery and violent, boiling with tiny breaks in the rules that keep it stable. A world that erases information, the math hints, is a world that cannot hold itself together in the calm way ours clearly does. Most physicists fight so hard against losing information for exactly this reason. Pulling that one thread threatens to unravel the whole cloth, taking prediction, cause and effect, and even the quiet stability of empty space down with it. Now bring it back to you, sitting wherever you are. The reason your world feels solid and reliable, the reason tomorrow follows sensibly from today, the reason the ground stays put and the sun rises on schedule, all of it rests on the universe keeping perfect records. The black hole information paradox is a stress test on that foundation. It found the one place in all of reality where the record might tear, and it asked whether the tear is real. So far the fabric is holding. The answer, as far as we can tell right now, is that the record holds. The rescue works, at least in the model universes where we can check it carefully. The universe seems to guard its memory even at the throat of a black hole, even as the greatest trap in the cosmos boils away to nothing. Reality, it appears, refuses to forget. But we have only peeked through a keyhole. We proved it in simplified worlds, and not yet in the full, sprawling universe we actually live in. The deepest version of the question is still open, still waiting, still able to surprise us. And the pieces that remain unsolved reach into the very nature of space, time, and what reality is made of. The frontier is still out there, and it is wilder than anything we have touched so far. So where does this leave us, standing at the edge of the deepest puzzle in physics? We began with a simple horror. A black hole swallows a star, a book, a person, then slowly evaporates into a faint glow and vanishes, seeming to erase everything it ate. That single worry, chased honestly, forced us to rebuild our picture of reality from the ground up. Look at how far the chase carried us. To save the information, we learned that a black hole stores its memory on its surface, not in its depths. We found that our whole universe might be a hologram, a rich inside world written on a flatter boundary. We watched wormholes grow from plain gravity and reach into the dark to rescue trapped secrets. We saw the inside of a black hole fold quietly into the light escaping it, and we watched distance itself dissolve into a web of quantum threads. Each answer was stranger than the question that came before, and yet the story is far from finished. The greatest results so far live in simplified model universes, clean and controlled, cousins of the real thing. Nobody has yet solved the full paradox for a true black hole hanging in our own messy growing cosmos. That calculation, the real one, for the real sky, is still unwritten. It may take a whole new theory of gravity and quantum rules combined, the theory Einstein chased and never caught, to finish the job. Deeper puzzles wait inside the winds. Physicists still argue about what the replica wormholes really are. They still debate exactly how a piece of information crosses from deep inside a black hole to the glow outside step by careful step. They still wonder what it truly means for space to be woven from entanglement, and what lies beneath even that. Every answer we found opened 3 new questions, each one taller and stranger than the last. That is the honest, thrilling truth of this frontier. We are standing in the middle of the story, in one of the great unfinished adventures of human thought, with the biggest chapters still unwritten. The people who will write them are out there right now. Some of them have not been born yet. One of them might be listening to this. Think about what that means. 100 years ago, we did not even know black holes were real. 50 years ago, we learned they glow and die. A few years ago, we finally caught the first hard proof that they hand their secrets back. The pace is quickening. Each generation pries loose a piece of the puzzle the last one thought impossible, and the prize at the end is nothing less than the deepest rulebook of existence. Solve how a black hole keeps its promise, and you may finally learn what space is, what time is, and what reality is truly made of at the very bottom. The dying black hole is a keyhole into that hidden layer, and we have only just pressed our eye to it. The universe threw us its hardest riddle, wrapped inside its darkest object, guarded by its strongest gravity, and piece by piece, against all odds, we are solving it. The trap that seemed to erase everything may turn out to be the very thing that teaches us what everything is, and the light is still leaking out, waiting to be read.